Okay, so what we want to do is we want to hit, in our talk now, we want to get to the next level of languages. But I wanted to do just a little brief review of when we talked about regular languages. I'm going to think of, here's an example of a really simple regular language. And I just want to talk about the topic of how languages and grammars match.
I have one doubt, like,
Oh, sure.
I just wanted to know what's the difference between a context-free language and a regular language exactly. Means like, with a regular language plus a stack gives us a context-free language.
Context-free language, right?
Yeah.
So a language that actually, you know what? I'm going to briefly describe regular, then context-free, and then what I'm going to today. So, okay. So here's an example of a regular language. This is probably the simplest language in the world. Our alphabet is A and B. If you read we start in this state. If we read a B, we stay here. Once we read an A, we jump to this state. And now if we read A's or B's, we just stay here. And I'm going to make this state the yes state. And this state will be a no state. So if you describe this in English, what is this? The language that has what property? All the words have what property? So basically, we're starting here. If we read a bunch of B's, it's no good. Then eventually we read one A, and then if we read A's or B's, it stays good. So what language is this? It's a two-state automata. So it's basically the language of words such that W has at least one A. Right? So it's pretty simple language. So for example, B, B, A, B, this would be a yes, because it has an A. If it was just B, B, this would be a no. Our machine has to answer no. So as long as there's one A, we answer it. Now what if we were to write a grammar for this language? How would we write the grammar? So the grammar would be, and the reason I'm going through this is we're going to define context-sensitive languages by grammar. We'll define it two ways, but one will be by grammar. What we can do is we can write a grammar for this by saying this state. So remember, like a grammar was like we were saying with the English sentences, there was a sentence is made up of a subject and a predicate, and then we made a definition of what a subject is, and then we made a definition of what a predicate is, and we said if the subject comes before the predicate, we say yes, it's a sentence, otherwise we say no. So it's kind of like that. We're going to write a grammar. We're going to say S becomes either, if we read, so basically we're going to pull the grammar out of the machine we're designing. So why don't we do this? Let's relabel these states. We'll say S is our start state, and we'll just make up a letter for this. Let's say X. This is state X. So when we're starting, before we do, like I said before, we had a B, B, A, B, we would answer yes. B, B, we would answer no. So when we read a letter, and maybe reading that letter, we move to a different state. We start in state S. S is the first letter of the word start. So we start in state S. If we read a B, what state do we go to? If we read
Same state.
Same state. So we'll say that an S can be read a B and then go back to the same state. If we're in state S and we read an A, we now go to a different state, a state called X. So we can say, or we read an A and then go to state X. Okay, now we have to define the state of X. So like assuming you started here, what would happen? So X ends up being, if we read an A or a B, we stay in state X. So if we read an A, we just expect to see an X come after that. If we see a B, we expect to see an X come after that. And we could also say if we see nothing, that's okay, epsilon meaning nothing. So this is actually the grammar for this language. And you can draw the grammar by saying, the grammar could be, these are now called productions, and these productions we can kind of get out of the machine we're designing. the state that we're in the finite state machine. And later on, we'll add more equipment, maybe the state we're in plus the values of our memory might tell us what the next state to jump to, but effectively, these are just states. So so really, this picture and this grammar really are describing the same thing. This is a picture that says we start in this state and we read A's and B's and it tells us where to go. And then these productions are saying that, kind of saying we are in this state. If we see a B, we stay in this state. If we see an A, we jump to another state. Then we have to describe each of those states that we jump to. Okay, so now, so this is an example, since we were able to define this language with a state machine, and it's actually really simple, two-state machine. This is a regular language. We didn't need any memory for it. If we're forced to use a stack, so if we had a state machine with a stack, if we had a language like an expression, I'm trying to keep this as simple as possible. An expression is equal to an open paren with an expression and a closed paren, or an identifier, or an identifier followed by an operator followed by an identifier. So this would be an example of a language where, for example, we could say expressions are like A plus B, that's an expression. Open paren A plus B, that's a yes. Open paren A plus B times C, that's an expression. These are things we would answer yes or no to. So if we were to define the grammar for this, we would say an expression can be defined this way. We would say identifiers can be A or B or C or A or B or C. And operations can be plus or minus or times or divide. And now we've just defined a grammar for all different types of expressions. We wouldn't want to accept an expression like this, open paren A, closed paren, times, plus C. This would be nonsense to us. This we would answer no, because it doesn't meet that grammar. If we were to build an automata to keep track of all the things that it requires yes and no's, we're going to have to keep track of, for every open paren, there's a corresponding closed paren. And there could be many of these, infinitely. We could say open paren, open paren, open paren, open paren, close, 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 close. This would be an expression in our language, as long as these match. 1, 2, 3, 4, 5, 3, 4, 5. As long as they match. If they don't match, then we'd say, oh, that's no good. The open paren, closed parens are wrong. So this ends up being, in order to build this language, a machine that can say yes or no to all of these, we would need a machine that, as we're reading these, we're hopping to we're either staying in a state or hopping to a new state, but we would have to record how many open parens we've seen by pushing them onto a stack and then popping them off when we see closed parens. So this ends up being a context-sensitive grammar, therefore for a context-sensitive language. And what actually makes this context-sensitive is the fact that this open paren must correspond to this closed paren. That's going to force us to have to use a stack. So, again, we haven't started talking about today's topic, which is context-sensitive languages. We just want to kind of build towards that. If you were given a language, I want to talk about, if you were given a language like this, a series of A's followed by an equal series of B's, where I is greater than 0. If you were to build a machine that would accept this language, what I mean by accept this language is I give you a string, you have to answer yes or no, is it in the language. So for example, A, followed by B would be a yes. Right? because the number of A's, the A's come before B's, and the number of A's and B's match. If I said A, B, B, A, what would we answer? No. The number of A's and B's match, but the order where the A's all have to come first and the B's have to come second don't match. So in that case, we would say no. Okay, so we get the idea. How would we do this? Can we come up with a finite state machine that doesn't use a stack, that can answer yes and no in every case? So, can you think off the top of your head? So the finite state machine might look something like this. We're in a state where we're going to start reading A's. So we would, well, I think we've talked about this before. We read an A, which goes to a state, that means we've read one A. We read another A, we go to a state, that means we've read two A's. We go to another state that says we've read three A's. Then if we read one A, we have to read exactly one B, and that becomes a yes state. If we read two A's, then we have to read exactly two B's, and this becomes a yes state. And do this forever, but this is going to be an infinitely many number of states, not a finite. So the only other thing we can do, well, if we had access to some memory, we could say every time you read an A, you start in this state, every time you read an A, we read an A and we jump to a state that says we've read an A. You read an A, and every time you read an A, you add one. So we increment a counter. Then we read a B, and we decrement the counter. And every time we read a B thereafter, we decrement. So if we had a counter, it's a two-state machine with a counter. Okay. Then we also said, when we were talking about context-sensitive, context-free languages, we said that instead of having a counter, if we could push things onto a stack, and we can only read the element on top of the stack, not perform mathematics on the data, and not let the value go off to infinity. If we had a finite amount of storage, that would be a limited version of memory that we can use. And that would have, if we had a finite state machine plus the use of a stack memory, which is a lot less powerful than actual memory where we can read and write from. Then the languages we can build using that equipment were called context-free languages. But what if you said, okay, I know how to build a context-free, I know how to build a push-down automata for this language. And I just wrote it out. It would be a two-state machine, and then we push A's onto the stack and pop B's off of the stack. What if someone said, I think I know a way to build a regular, I know a way to show that this is a regular language. And what we're going to do, they say, I think it can be done, a finite number of states with no stack. Could you make an argument that it's not possible? Is there any way to say that there's no finite states, finite state machine that's not using a stack that could do this? So there's this thing called a pumping lemma, which we're going to use to prove that this language could never be done with a finite state machine. So the pumping lemma for regular languages says this. If somebody comes along and says, I've built a finite state machine that will always answer yes or no for any string, whether it's in this language or not. Let's say their state machine, they say they have an n state machine. And n could be some really large number, like 1 million or something like that. But it's some finite number. They have an n state machine. Then wouldn't the word A to the n plus 1, B to the n plus 1, what would the answer to that? So if somebody claims they made an end state deterministic finite automata that will answer yes or no for all of these words. And you say, okay, what would happen if I gave as input the n plus 1, a to the a n plus 1 times, and b to the n plus 1 times? What would happen? Well, somewhere in there, so I'm not going to give the formal definition of the pumping lemma, I'm just going to try to explain what it is. Somewhere in your state machine, or their state machine, they would have a start state, then they'd start bouncing around through different states. They'd read letters and they'd start bouncing around. They're going to go somewhere, right? And there's a total of n states. So after they've read n plus 1 A's, could they have gone to, could they ever have, is there a way that they could not have found themselves back in a state? Could they visit a brand new state every time? So if there's n states, and you start here, and then maybe you read an A, and you go here, and then you read an A, and you go here, is it possible to read n plus 1 A's and always visit a brand new state every time? Or would you have to re-land on a state you've already visited?
Every new state?
So if the state machine has n states in it, you know, 1, 2, and it goes all the way up to n. And I've read every time, so the way a finite state machine works is every time you read a letter, you hop to a new state, or maybe you stay at the same state. You could stay at the same state. But you always jump somewhere. So the question is it possible to read n plus 1 A's, and every time I read one, I jump to a brand new state I've never been to before? Or will I have to at least once go back to a state I've been to before? Right, so I would have to go back. At some point, I went through a loop. I either went from here to here, like maybe I went from here to here to here, then to here to here, but somehow I had to have reappeared at a state I've already been to. Because the machine only has n states, but I have to go to n plus 1 places, so I must have repeated one of those places. So somewhere in that state machine is a loop. And the size of the loop is at least 1, even if it looped to itself. That means that the size is of at least 1. So the size of the loop is somewhere between 1 and n. So in the formal definition, they're basically saying that any word that's in the language, so like a word, for example, could be a word could have a U part, a V part, and an X part. And somewhere there's going to be a V part, which the size of the V part is greater than or equal to 1. The V part is greater than or equal to 1, and the U followed by the V part is going to be less than or equal to n. So there's some part maybe in the middle of your word that we're going to let be as big as all the number of the states of your machine is going to make that V part is something that causes a loop in your finite state machine. What we could then do is we could say if a word, which is made up of 3 parts, U, V, W, if this is in your language, then the word U, V, V, W has to also be in your language. Because the V part, the V component of your word, is the part that made the loop. So there's, without a doubt, and I think sometimes this notation gets a little confusing, but so I think it might be better to just use an example like this. If you have an n-state machine, and I put a string on it that has n plus 1 A's, after you've read all n plus 1 A's, without a doubt, you've done a loop. You've had to have done a loop. We haven't even seen B's yet. Whatever that loop part is, we can run that loop and I guess that's why they call it the pumping lemma. You can keep pumping that loop. You can keep running that loop as many times as you want, and the machine will always answer yes. But the problem is you'll now have more A's than you have B's. So the argument goes like this. If somebody says, I have found a machine that has n states, and n could be at a really high number, 10 million, 100 million. I have found a machine with n states that can answer yes or no to this language and never use a stack. You could always say, well, what would happen if I put n plus 1 A's followed by n plus 1 B's onto a machine? Without a doubt, it will run a loop while it's just reading the A's. And then that loop, you can run that loop over and over and over and never add any more B's, and then you'll always have more A's than B's. So that ends up being, this is the pumping lemma for regular languages, and there's a very similar one for context-free languages. So if somebody comes along and says they have found a push-down automata, they found an n-state push-down automata. Someone comes along and says they have found a push-down automata that can tell whether or not a language is, let me first give an example. This might be, let me come back to the pumping lemma for context-sensitive languages, context-free languages. Let's take this language into consideration. This is going to be, now we're finally talking about context-sensitive languages. But let's explain why this is a context-sensitive language. This is a language where the acceptable words are like, it's a series of A's followed by a series of B's followed by a series of C's, where the number of A's and the number of B's equals the number of B's, and the number of A's and B's equals the number of C's. So for example, A, B, B, C, C is a yes. We have A's followed by B's followed by C's, and there's two of all of them. A, B, C, what would that be? Yes or no?
Yes.
That would be yes, because we have A's followed by B's followed by C's, and the numbers match. So that would be yes. Okay. What if we had A, B, B, C, C, C? Would that be a yes? So it's no, because although we have A's followed by B's followed by C's, the numbers don't match. We have 1 A, 2 B's, 3 C's, so that's a no. And A, B, C, C, B would also be a no, because the number of A's, number of B's, and number of C's, there's two of all of them, so that's good. But there's a B after a C, so that's no good. We have to have the order, the A's, and then the B's, then the C's. Okay. If somebody came along, and this is just an extension of that last pumping lemma for regular language, if someone came along and said, I have designed a push-down automata, they're claiming L is context-free because they created an n-state push-down automata. An n-state machine with a stack that if you gave anything in here, any word that meets this, they can answer yes, and otherwise they'll answer no. So the question is, well, first of all, could you think of, just off the top of your head, can you think of a push-down automata? Like, describe in English how it would work, that would answer yes or no for this language. We might think, we'll read A's and we'll push the A's onto the stack. Then while we're reading B's, we'll pop the A's off the stack to make sure the counts are fine. But now we start reading C's and the stack is empty and we don't know how many A's or B's there were. So then maybe something else we could do. Can we push A's onto the stack, then maybe push half the B's on top of the A's and then pop off the other half? You know, is there any... There might be some way with a stack that we could do this. It might take a little thinking. But if someone came along and said, I've done it, I have a end state push down automata for this language, we can actually, using a very similar pumping lemma, we're just going to call this the pumping lemma for context-free languages. What we could do is we could say, if somebody took a word, like let's say A, B, 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 C, C, C. Suppose somebody comes along and says, I have an end state machine that, if somebody says I have an end state machine that puts items onto the stack and then pops items off of the stack later on, there's going to be at least one point in our word, if we chose a word like a word of A to the n plus 1, B to the n plus 1, C to the n plus 1, and put that on their machine, there's going to come a point where they're using the stack, they're pushing things onto the stack. So the word W might look, their state machine might start at a certain state, it'll go somewhere, then hit a state where things are being pushed onto the stack, then another part of the word, then another place where things are being popped off of the stack, and we answer yes. So somewhere in that state machine this is happening. So let's say the part where they're pushing things onto the stack happens while we're reading the A's. Then whatever we're pushing onto the stack, once we hit a loop, we can pump that as many times as we want. And the corresponding part would have to be pumped also. But this part of the word, maybe it contains A's, maybe it doesn't contain A's. If this part only contains B's, and this part contains C's, then we could take a word of n plus 1 A's, n plus 1 B's, n plus 1 C's, and then we could add more B's and more corresponding C's, leaving the count of A's alone, and then we would be answering yes to a word that's not the language. If the part that's being looped contained A's and C's only, then we can make the number of A's and C's be greater than the number of B's. And if the part that contains, the two parts that get pumped contain A's and B's only, we could have more A's and more B's than we have C's. If the part of the language that gets pumped, that pushes things onto the stack, contain both A's and B's, then we'd have words that are of the form, you know, A, B, 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 then A, B, 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 because we keep looping that part of the word, and those would be no good. So this is just a very informal description of the pumping lemma. I'll go over, or in the class notes we have a more formal definition, but it's just breaking down a word like this, into, so using an example where each of these letters have more occurrences of them than there are states in your state machine, is going to force two parts of the push-down automata to be able to repeat over and over and over. Basically the part where you're pushing things onto the stack and a part where you're popping things off of the stack, those two parts we're allowed to repeat as many times as we want. And that's going to cause the number of A's, B's, and C's to go out of balance. But yet this push-down automata will keep answering yes. So that means the push-down automata doesn't exist. So this is not true, and therefore this is not considered a context-sensitive language. So what we're basically saying is we could never design a finite machine with a stack and nothing else that can answer yes or no to this. We'll always need something else. Can you think of another piece of equipment we could add that we could make this work? So, sorry?
D.
The what?
If we add like A, B, C, and D, then...
Well, no. What I'm saying is if let's say as we're reading words and trying to answer yes or no, if we're reading here, we can push A's onto a stack. Every time we read an A, we push an A onto the stack, read another one. Then we read B's, we start popping the A's. But now when we get to here, we've lost count of how many A's or B's we have. And we have to make sure we have exactly 3 C's, and we don't have any way to remember that. If we had another piece of equipment, maybe a second stack, could we then build a machine like with a finite state automata and 2 stacks that could answer yes or no every time? What we could then do is we could push A's onto the stack, and let's say we had a second stack. Every time we see a B, we pop an A off of this stack and maybe push it onto this stack. And then we read another B, and pop this one off and push it here. And then we read another B and we pop it over here. And now we have a count for how many C's we should expect. And then when we read C's, we pop stack number 2, and then if both stacks are empty, we could answer yes. So a finite automata with 2 stacks, we could find this language. But the finite automata with just 1 stack, there is no way. So we showed by the pumping lemma, there is no way to build a push-down automata to accept this language. So we have to give this type of language a new name. So I already wrote the new name up on top, context-sensitive language. So if we were to write a grammar for this language, how would we do it? Or if we wanted to build a state machine, or yeah, let's say we wanted to write a grammar for this language, how would we do this? We're starting in a state. Now when we write grammars, it's like here's a start state. And this is kind of the reason why I talked about grammars earlier. If we wrote it as a grammar, we're in a start state. So we have to build some kind of a machine, and we actually realize we can build a finite state machine with 2 stacks that can answer yes or no to this. So these productions are going to be a way of describing I'm in this state, and the stack has this value, so therefore I'm going to jump to this state. And then whatever state we jump to, we'll write another production for that one. So, like anything off the top of your head, what I kind of remember when the first time I heard this problem, I thought I started coming up with a grammar for it. But is there a grammar? What would you think? The start symbol, we're starting, meaning we haven't read anything. What do we expect to see? Well, we expect to see a bunch of A's, followed by a bunch of B's, followed by a bunch of C's. So we might do something like this. A, capital A, which we're going to define later on, and then a capital B, and then a capital C. So, and then we could define A's, B's, and C's later. Suppose we then said, okay, I'm expecting to see a bunch of A's, followed by a bunch of B's, followed by a bunch of C's. And then down here I say, okay, here's what a bunch of A's is. It's a little a, followed by maybe more A's. Or maybe just one little a. And what's a B? It's a little b followed by more b's, or maybe just a b. And what's a c? A c is a little c followed by more c's, or maybe just a c. Is this grammar, does that correspond to this language? Well, no, this grammar actually says I'm going to see a bunch of a's, and a bunch of b's, and a bunch of c's. But it doesn't say the number of A's has to match the number of B's and match the number of C's. So for example, this grammar would successfully parse A, B, B, C, C, C. Because I'd say, does this word become an S? Well, it does if this can be broken up into an A section, a B section, and a C section. What is an A section? An A section is an A by itself, or maybe an A with more A's after it. Yeah. And that's true. So this would be considered an A part, an A piece. Now the question is, can this part be considered a B piece? Well, let's see, what is a B? A B can be a B by itself, or it could be a B, and then go back here and look for more productions. So, this piece turns into a B followed by a big B, and then a big B becomes a little b, and becomes 2 B's. So that's yes, this part is a B part. And then the same for the C part. But we're not keeping, we've lost the part where we keep count, right? So this grammar here, is not the grammar for this language. It's the grammar for a language where there's a bunch of A's followed by a bunch of B's followed by a bunch of C's, but the numbers can be anything. How would we write a grammar that forces the counts to stay the same? And if you come up with this, you kind of know why it's context, or maybe the hint would be it's context sensitive. What we don't want to do, because we're required for the counts to be the same, we never want to define A by itself. We don't want to have a rule like this. A equals little a followed by big A. We never want to have this because now we can have a random number of A's. We want to somehow say, if you see an A, there has to be exactly one corresponding B after it and exactly one C after it. How can we force that? Right now, what we've done so far with regular languages and context-free languages, we've always started with kind of our start state and then said, here's the parts we expect to see after it. And then we gave a breakdown of those parts, described in a breakdown of those. And they were always described separately, independent of this thing. Like the description here, when I say A is little a followed by big A, I'm describing A. I'm not saying there has to be a B or C after it. I'm just describing A's separately. So, and kind of context-free from the other parts. But if I wanted to enforce a rule that says A, the number of A's has to equal the number of B's, has to equal the number of C's, what would my next line be? The next rule. What if we did something like this? A, B, C can be thought of as a little a followed by a big A, a little b followed by a big B, and a little c followed by a big C. If we did that, we're now, like kind of described in English, what are we doing here? We're saying this piece has to be defined together with each other. A's can't be defined separately. An A section must always be followed by a B section, which must always be followed by a C section. And they have to be done in such a way that each one spits out exactly one A, one B, and one C. Now the question is, how do we make the big A and the big B and the big C spit out more A's and B's? We need a rule like a little a followed by a big A, a little b followed by a big B, and a little c followed by a big C can be two A's with an A after it, two B's with a B after it, two C's with a big C after it. Now, with these two rules, we could parse a word like, A, B, 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 C, C, C. This we should answer yes to. So we're saying to ourselves, does this whole thing become an A followed by a B followed by a C? Well, maybe it does. What is an A followed by a B followed by a C? An A followed by a B followed by a C can be a little a with an A thing, a little b with a B thing. So this could parse into, if this can be considered an A, and this piece can be considered a big A, and this be considered a little b, and this part be considered a big B, and this part be a little c, and this part be a big C, if that's true, then this original word is a yes, otherwise the answer is no. Well, what is an A, little a followed by a big A, little b followed by a big B, little c followed by a big C? Well, we have a rule here. That can be considered if it's an A and an A followed by a big A, a B followed by a big B, a C followed by a big C. Is that what we have here? Well, can an A, can this piece be considered, can this piece be considered a big A and this piece be considered a big C, and so on. So we can inductively create a grammar like this. And the way this was written, because the A and the B and the C were defined together, we forced the number of A's and B's and C's to match. So it's not like one of these can kick out as many A's as they want. They're forced to match. So we need a name for this type of language. And if you had to think of it, so basically, the name kind of comes from the way the grammar is written. Instead of what we've had so far is we would always say we start here and then we describe the parts of what it is we're parsing. And then we individually describe those parts. That's what we've done so far. Now we're saying, I want to describe the parts, but the parts are in context to each other. This A section must appear before a B section, which must appear before a C section. It must appear in this order. Otherwise, the A part is no good. So the stuff that's on this side of the arrow is actually related to each other. So the context they appear in matters. So they could call it context mattering languages, or context. They call it context sensitive languages. So you're making definitions here that have to appear in a certain order. Okay. So kind of, there's a few ways to describe a context-sensitive language. One way is context-sensitive language. I call them CSLs now. A couple ways to describe them. One, accepted, meaning we'll always answer yes if you give a word that's in it. Accepted by a 2-stack push-down automata. With 2 stacks, the push-down automata will accept it. Another way to describe a context-sensitive language is a grammar where the things on the left side are in relation to each other or in context to each other. Where if you ever have an alpha, if you ever have a production that goes like this, alpha produces beta. The alpha part is less than or equal to the beta part in size. So the part on the left side can never expand bigger than the right side. And we kind of just saw that in our example, that what was on the left side the right side could get wider and wider, the left side wouldn't get wider. A third way to describe this, and this is really another way of saying part 1. A state machine, a finite state machine, so a finite state machine with linear storage. Now, if you think about it, if you had 2 stacks, suppose you had 2 stacks to work with, you could push stuff onto one stack, pop stuff, or push and pop onto a stack, and you could take stuff from one stack and push it onto another stack, right? But theoretically, if we took these 2 stacks and glued them side by side, they would look something like this. 2 stacks would look like this. Right? We're pushing stuff onto the stacks and popping it off. And when you pop off of one stack and push it onto the other one, aren't you just doing this? Aren't you just kind of moving it over? So if you took your 2 stacks and put it together, if you had, let's say you had A, B, C, X, Y, Z. And your 2 stacks look like this. You have 6 memory cells. If you make a move where you push a C off of this stack and push it onto here, you now have this, right? But if you think of the two stacks as just pushed together, really nothing's changed. So technically, two stacks have the computing equivalency of a block of memory, right? Now, because our state machine, every time it moves to another state, we can either add a piece of memory, change a piece of memory, or delete a piece of memory. The size of our memory will never get bigger than the number of letters in our word. So we're going to call this a linearly bounded storage. So I'm going to put in the word bounded storage. Okay. So those are three different ways to describe a context-sensitive language. Context-sensitive language can be accepted by a two-stack push-down automata. Context-sensitive language is when you go to write out its grammar, there's some property about the language, like keeping counts of where things are, or things are only acceptable if there's stuff after it, or things are only acceptable if there's stuff before it. Where these things appear are in context to other things in the word. That's going to force us to write a production, like we said, where it was, A, B, C became something. I couldn't define A's and B's and C's alone. They can only be defined if they're next to something else. So we have to write a grammar that way, and we also want the grammar, we don't want the thing that's what it becomes being something smaller than what it was. That would mean we would need storage that's bigger than the word that we had. And then actually this is the more official definition of what a context-sensitive language is. It's accepted by a finite state machine that has a linear, a piece of storage that is equivalent in length to the input word. Okay. So, and then what we'll talk about next time is the topic of a recursive language. We'll define this next time, but another definition could be for context-sensitive languages. They are recursive. And what recursive means, and this we'll go over an example next time. Basically, yeah, what I'm going to say is a recursive language is, well, just one second. A recursive language would be a language in which if I give you an input where the answer should be yes, your machine can always either answer yes or answer no. If a language is not recursive, we might be in a situation where if I give you a word that's in the language, your machine will answer yes, but if I give you a word that's not in the language, your machine may go into an infinite loop. So sometimes the answer never comes out. Sometimes you get a yes, and sometimes you get no answer. But if you always get a yes and always get a no, that language is called recursive. And context-sensitive languages is the equipment you need, whether you use a linear bounded tape or two stacks. You'll always be able to create recursive languages. Okay, all right, great.